Welcome to another deep dive. This time, we're going to be tackling something pretty interesting, I think. Electromagnetic waves.
Oh, yeah.
It's one of those topics that can seem kind of abstract,
Right.
but they're actually behind so much of the technology and just like the way the universe works.
Yeah, definitely.
We're going to be taking a look at an excerpt from a physics textbook, actually.
Okay.
Chapter 8, which is all about electromagnetic waves. And I thought it'd be fun to sort of go through and unpack some of the key ideas,
Sounds good.
especially, for people who maybe haven't thought about physics in a while or,
Right.
maybe just want to learn something new.
For sure.
So the textbook kicks off by talking about this problem that scientists had with Ampere's law.
Okay.
Have you heard of Ampere's law?
Yeah, so Ampere's law, it basically describes how electric currents create magnetic fields.
Right. It seems pretty straightforward at first glance, right?
Yeah, totally.
If you have electrons flowing through a wire, you get a magnetic field around it.
Exactly.
But then they started looking at charging capacitors,
Uh-huh.
and things got kind of weird.
Yeah, the math just didn't add up.
Right. It was like there was this missing piece of the puzzle.
It was, and it was actually a physicist named James Clerk Maxwell who came along and figured it out.
Oh, yeah, Maxwell. He's like a legend in physics, right?
Yeah, one of the greats.
So what did he figure out?
Well, he proposed this radical idea that maybe changing electric fields could also create magnetic fields.
Wait a minute. So you're saying it's not just about electrons physically moving.
Right. It's like even the electric field itself changing is enough to create magnetism.
That's wild.
It is. And he called this missing piece displacement current.
Displacement current. And
You know what's really amazing is that this insight, this little tweak to the equation, ended up leading to one of the biggest discoveries in physics.
really? Which one?
Electromagnetic waves.
No way. So that's how we figured out that light is actually an electromagnetic wave.
Exactly, because before that, nobody really knew what light was made of.
Yeah, I remember learning about that in school. It's like light's this wave, but it doesn't need a medium to travel through?
Right, unlike sound waves, which need air or water or something.
So are you telling me that the light we see from the sun has traveled millions of miles through the vacuum of space to reach us?
That's exactly what I'm telling you.
Wow, it makes you realize that we're surrounded by these invisible waves all the time.
It really does. And what's even cooler is that what we see as light is just a tiny sliver of a much broader range of waves.
You mean like there's more than just the colors of the rainbow out there?
Oh, yeah, way more. We call this whole range the electromagnetic spectrum.
Right, the spectrum. I remember seeing those charts in textbooks of all the different types of waves.
Exactly. And we're going to dive into that spectrum next. But first,
Yeah, let's take a quick break and we'll be right back.
sounds good. All right, so we're back.
And we're ready to dive into that electromagnetic spectrum.
Yes.
I'm actually curious about something, though. You mentioned that light is an electromagnetic wave.
Uh-huh.
But how are these waves actually created in the first place?
Well, that's a great question, and it might surprise you to learn that simply having electric charges isn't enough.
What do you mean?
Well, like a stationary charge, just sitting there, it'll produce an electric field,
Okay.
but it won't create an electromagnetic wave.
So what does?
It has to be accelerating.
Accelerating.
Yeah, it needs to be speeding up or slowing down or changing direction.
So it's not just about the movement of electrons, then?
Right, it's the change in motion that's crucial.
I see. So it's like shaking a rope. If you just hold it still, nothing happens.
Exactly.
But if you give it a flick, then you create a wave that travels down the rope.
Perfect analogy. And just like with the rope, the frequency of the shaking determines the frequency of the wave.
Okay, so to create a specific type of electromagnetic wave, like a radio wave, you need to control the frequency at which charges are accelerating.
That's right, and that's how we can encode information onto these waves.
So that's how we send radio and television signals.
Precisely. And it's not just radio and TV either. We use this principle for all sorts of wireless communication.
Like cell phones and Wi-Fi?
Exactly.
It's amazing how we've harnessed these invisible waves to connect the world.
It really is. And, it took some time for scientists to really figure all of this out.
Oh yeah, didn't Maxwell make his predictions back in the 1800s?
He did in the 1860s, to be precise.
So how did they actually prove that he was right? I mean, did they have the technology back then to generate and detect these waves?
Not really. It took a few more decades. Then a very clever physicist named Heinrich Hertz.
Hertz?
Yeah, he came up with this ingenious experiment in 1887 using a spark gap.
A spark gap, what's that?
It's basically a gap between two electrodes where you can create a spark by applying a high voltage.
Okay.
And Hertz used this spark gap to create radio waves, and then he used a loop of wire with a tiny gap to detect them.
So he built the first radio transmitter and receiver?
Essentially, yes.
Wow, that's incredible. So Hertz was the one who actually proved that electromagnetic waves exist.
He was, and he showed that they behaved just like light waves. They could be refracted and diffracted.
That must have been a huge moment for physics.
It was a game changer. It solidified Maxwell's theories and paved the way for the development of all sorts of technologies.
Like radio communication and radar.
Exactly.
But the story doesn't end there, right?
Of course not. 7 years after Hertz's work, an Indian physicist named Jagadish Chandra Bose demonstrated the generation and transmission of even shorter wavelengths.
Wow. So they were really pushing the boundaries of what was possible.
They were, and at the same time in Italy, Guglielmo Marconi was building upon Hertz's work, transmitting electromagnetic waves over longer and longer distances.
Marconi, he's the one who's considered the father of radio, right?
That's right. He sent the first successful transatlantic radio transmission in 1901.
It's hard to imagine a world without wireless communication today.
I know, right? And it all stems from those early theoretical insights and experimental breakthroughs.
So we've talked about how these waves are created, the different types that exist, and how they were discovered.
We have.
What else is there to learn about this invisible world?
Well, we've only just begun to explore the fascinating ways that these waves interact with matter, but we can dive into that.
Yeah, let's do it. I'm really curious to hear more about that.
All right, let's go.
So we've talked about how these waves are created, the different types that exist across the spectrum,
Yeah.
and, how they were actually discovered and all that.
Right.
But I'm really curious about how they interact with, matters. Do they just pass through everything, or?
That's a great question, and it's one that has fascinated scientists for a long time, and the answer is it's complicated.
Oh, come on.
It really depends on the wavelength of the wave and the properties of the material it's hitting,
Okay, so different wavelengths behave differently when they encounter an object.
Exactly. Think about visible light for a second.
Okay.
When light hits an object, some of it gets absorbed, right?
Yeah.
Some of it is reflected, and then some of it might even pass right through.
Right, which is why we see different colors and some things are transparent.
Exactly. A red apple looks red because it absorbs most of the wavelengths of light except for red.
Right.
Which gets reflected back to our eyes.
Okay, and a window pane is transparent because it lets most visible light pass through.
Precisely. And those same principles apply to other parts of the electromagnetic spectrum, but with some pretty interesting twists.
Okay, so give me an example.
We'll take radio waves, for example.
Okay.
They have much longer wavelengths than visible light.
Uh-huh.
And that gives them the ability to diffract or bend around obstacles.
Oh, so that's why you can pick up a radio signal even if you're not in direct line of sight with the transmitter.
That's exactly right. The waves are basically curving around buildings and hills to reach your radio.
That's cool. So if longer wavelengths could diffract, what about shorter wavelengths like X-rays?
X-rays are different. They have incredibly short wavelengths and enough energy to penetrate through lots of materials that are opaque to visible light.
So that's how they take pictures of the inside of our bodies.
That's right. The X-rays pass through soft tissues, but they're absorbed by denser materials, like bone.
So it's like we're using different parts of the spectrum to see things that would otherwise be invisible to us.
Exactly. And the way that different materials absorb or transmit different wavelengths, that's what makes the electromagnetic spectrum so useful.
In so many fields.
Yeah, in science, medicine, technology, you name it.
So we've got radio waves for communication.
Right.
Microwaves for heating. Infrared for heat sensing visible light. For seeing ultraviolet for sterilization.
Yeah.
X-rays for medical imaging. And gamma rays for cancer treatment.
It's quite a range, isn't it?
It's mind-boggling to think that all of these things are just variations of the same basic phenomenon.
It really is, and we're still discovering new ways to use the electromagnetic spectrum.
That's really exciting. Well, this has been an incredible deep dive. I feel like I've learned so much about, the unseen forces that are all around us.
Yeah, it's amazing how much is going on that we don't even realize.
Well, it just goes to show that the more we learn about the universe, the more we realize how much there still is to learn.
That's for sure, and I think that's a great place to leave it. So, yeah, thanks for joining us on this deep dive.
And remember, stay curious, everyone. We'll catch you on the next one.